parametric equations and polar coordinates. The part we're starting with is the parametric equation part. This is chapter 10. It's a couple of different ideas mashed together. But the basic idea is the back half of the class is going to be about doing calculus on functions with different variables than what we've been used to before. So we're sort of ramping up to the calculus of actual physics. That's kind of where we're going. The calculus of actual engineering, actual science, actual mathematics. So we're on a slow ramp. If you want to think about what's going on, we're slowly ramping up to multivariable or vector calculus. The things we're doing now are not that, but they're on the way there. Okay, so what is a parametric equation? 10.1. So the motivation for this comes from physical systems or any sort of dynamical system. And the idea here is that the original idea is imagine you've got a particle moving through space. So a particle moving through space, you can imagine an electron in an electric field or something like that, traces out a curve that it travels on, right? The path that it takes is a curve. There's some curve. So the particle travels along and it traces out some curve. So C is a curve, which you can think of as being the path of a particle. As time changes, the particle changes its position on the path. Right? At a given time t, the particle is here. At a different time, maybe it's somewhere else. There's a different x. At a different time. There's a direction of motion. Time evolves, the particle slides. This is directed. So the arrows are here to indicate that the direction of motion here is this. Now, in this sort of setting, I would really like to do calculus. Calculus is concerned with questions like, how far did the particle move? What forces are it under? How fast is it going? And to do that, I need to be able to do calculus on its pathway. Problem is C a function, or the graph of a function? That curve I wrote right there, if I want to do calculus on this, I'd really like this to be of the form y equals f of x, or x is equal to f of y. Is it? Why not? Vertical line test, and also, so the vertical line test means that y is not a function of x because of the vertical line test, right? And x is not a function of y. Sometimes we can cheat by saying x is a function of y, like a sideways parabola. That can't happen here because we also fail the horizontal line test. What I mean by that is, if you go through the curve, there are places where one x value gives you multiple y values, which means y cannot be a function of x. And there's places where one y value gets you multiple x values, and so it can't be a function of y. Okay, so that sucks, because that means I can't do calculus on this path. So the observation is, even though the path is not a function, the coordinates are still continuous. A particle moving in space doesn't, like, you get in your car and drive to school, you don't like warp, right? You continuously move through space. I mean, I hope you continuously drive through space when you're in school. If you don't, I'd like to know the trick. But particles moving in space move continuously. Paths move continuously. And so that means is maybe looking at the curve is the wrong question. Maybe we should be thinking about the path that the particle itself is making as it moves, instead of trying to think about it as one finished field. So the idea is that we think of x of t, y of t. We think of the coordinates as functions of time instead. I'll put this up higher on the board. I'm sorry. I'm not used to this full room. So what we're going to do is we're going to think of the coordinates as functions of a parameter. Now the parameter is not always time, but it's useful to think about the parameter as time because that grounds this in a physical analogy. So oftentimes we say t for the parameter, and most people, unless they're told otherwise, think about the parameter as time, at least in the beginning. So that means that we're looking at x of t, y of t. Where now these guys are the functions. The coordinates change as time changes. We're encoding the fact that there's motion going on in this setup. So any expression of this form is called a parametric function. Parameter is the variable that the system is evolving in response to. Okay? This is a parametric function. And the path that it traces out, in this case, if at some point this thing is located at x of t, y of t, this is called a parametric curve. So the parametric curve is the path that a parametric function makes. And you can describe things with parametric functions, you can't do otherwise. All right, so let's look at an example of a parametric function and the curve, the parametric curve that we get out of thinking about what the coordinates are doing. So the way these are typically presented might look something like this. Draw the curve traced out by x of t is equal to, what's the first example I did last time? Make sure I coordinate. So t squared y of t is equal to 1 plus t. And I'm going to fix some t values too, or t in the values between 0 and 2. So another thing you can do with parameters that you don't get to do oftentimes with graphs is I can specify a particular piece of a parametric curve by telling you what I want the parameter values to take on. Here you can imagine 0 seconds to 2 seconds. So this is normally called an initial value, and this is a final value or a terminating value for the parameter, and those correspond to points on the curve. Okay, well, let's draw it. We're going to get all middle school here and use a table. Because a table is something that you always have available on a question like this. You can always make a table to draw one of these graphs. And frequently, if you don't see the algebra, the table is the best way to go. Let's draw it. T, x of t, y of t. Oh, I don't know, since we're being lazy, maybe we'll write t. So we'll do 0, 1, and 2. Let's try to see if we can figure out what's going on without having to resort to using fractions in between. Although your job is always to use enough points to convince yourselves if the curve has the shape that it does, or to run off to Desmos and plug it in there. Yeah. Or whatever your favorite quick modeling program. Okay, so to get the x and y coordinates on the curve, we're going to plug the t values in over there. 0, 1 plus 0 is 1. So notice that gave us a point we can plot. So we start at 0, 1. Then I'm actually going to mark for myself that this corresponds to the value t equals 0 as a way of keeping track of if what I'm drawing makes sense or not. If you screw one of these points off and you end up with a curve that looks pretty nice because 1 point's way out here, probably you made a mistake when you're in the table. So anytime you can keep yourself honest, you should. So this is the t equals 0 point. At t equals 1, we get 1 squared is 1, and 1 plus 1 is 2. 1, 2 at t equals 1. Notice the t is basically disappeared now because we're just writing coordinates down. Finally, if I put in 2, 2 squared is 4, and 1 plus 2 is 3. Out here. Now, because the particle moved in time, I'm going to mark this curve with arrows so that I understand what direction the motion originally was. Now, I realize here I'm using the 1, 2, 3 infinity thing where it's like, look, I found 3 points, and so therefore I know the whole curve in between it. But I'm going to show you that this thing actually simplifies into a parabola. We're done with it. Okay, so what you should see when you look at that is, well, I don't know, maybe it's a parabola. I mean, after all, there's a t squared in here, so maybe the t squared behavior is somehow coming out in the way that the points are acting, right? If we're finished marking up the graph, this was the initial point because that's where the particle started. This is the final point because that's where it ended. So how can I get a more accurate description of how this curve works in regular old Euclidean coordinates? The answer is I could just use algebra. If I want to find a relationship between x and y, I have to do what's called eliminating the parameter. This almost always involves either algebra or fear of fears, trig identities. Yeah, not in this one though. This is just algebra. You realize the second half of this chapter is called polar coordinates, right? It's going to be all trig all the time. We'll talk about it when we get there. Okay, so in this particular case, we're not going to use trig because there's no trig. We use algebra. And when you're using algebra, you can set up substitutions. You have a relationship between x and t, and you have a relationship between y and t. So you can just do substitution. The easiest substitution to see here is that, well, if y is equal to 1 plus t, then t is equal to y minus 1. Right? I just solved this equation for t. Now, why do that? Because that lets me substitute into the equation for x and the t disappears. And there's no t anymore. If you take this and you substitute it into the expression x is equal to t squared, you get x is equal to y minus 1 squared. And y minus 1 squared is a parabola that opens to the right that's been shifted up by 1 unit. So this thing right here is the equation that this little curve sits on top of. And I want you to be careful about this. This parabola looks like this, right? It keeps going here and goes this way. So that parabola is a whole curve sitting in space and goes forever. This little parametric piece of it is just part of that curve. So when we do this, when we eliminate the notion of time from an equation like this, we're throwing information away. We've lost information here. We've lost the idea of motion. If we're not careful, we lose the idea of an initial and final point. I've lost any notion of how fast the particle was traveling. I've destroyed all the motion in the problem to record what the curve looks like. That's very important in some cases. Okay? But there's a sacrifice to doing that. Well, since I said I was going to do trig, we should do some trig now. So let's do another one of these with some trig so you can see how that kind of thing works. Okay. I should point out, like, one of the things that we're doing here is we're building up a setting that we can do calculus in. The goal is to do calculus on these objects. To use calculus to study the path of an object. If we study the path, we're studying things that don't care about speed, like curvature, for example. How fast the article is turning doesn't depend on how fast it's moving. But I also want to know about velocity and distance traveled. And all of that is going to depend on how fast the particle actually moves. So there's going to be two different calculus approaches to studying these things. One that studies the way that the particle is moving on the path, parametric calculus, and one that studies the path that it actually follows, which is just the regular calculus that we learned in Calc 1. Yep. You don't. Actually, so generally, these oftentimes are not solvable. So in many cases, when you're working in practice with these, it is not possible to eliminate the parameter in many cases. And in that case, you're just stuck working numerically. And you don't, you're basically numerically reconstructing the path out of the parameter. So like there's ones where you can have paths that mix sines and cosines together. They're like these really symmetric things, but they're, they twist around each other in these complicated things. And that might actually be the path the particle is following. You're never going to write a parameter eliminated version of that, right? It's a totally valid thing to do, but you're never going to be able to write down an equation that makes that. So yeah, so generally, as in most cases in calculus, one of the lies that we tell you is that we pretend that these things can all be solved analytically, like with formulas and exactness, when in practice, almost everything is done numerically. Because in general, there's no guarantee that this is even possible. Like if I put a t squared up here and some mixture of trig functions down here, that's a transcendental equation. There's just no way to untangle it. So, yeah. I mean, dude, this stuff is hard, right? They invented it for a reason. Don't complain to me. I didn't do it. Guys, those of you, I know, I can see the computer scientists here. What does this have to do with me? Well, guess who has to actually implement the crap that solves this stuff? Right. I'm going to work on video games. Okay, you know what a 3D video game engine does? It's just this. This is what it's doing in the background. It's this. I already created it for us. Yeah, who makes the money? The guy that makes the engine.
What if I just look it up on the
Programming by cut and paste. That's what it is. There's nothing else. Yeah. Okay, what are the okay, so let's look at this one. So here's one where this is a very reasonable thing to come up in practice. The idea that like functions that are defined in terms of trig functions, because if we're studying anything where things are evolving in terms of angle, now we should be thinking about t here as measuring the angle that a system is evolving, right? So this is a way of understanding as the angle changes what's going on. Comes up all the time in science and engineering applications that we work with trig functions. Okay, so let's do a table. And I'm going to remind you now, I haven't had a chance in this class yet, but one of the things you're supposed to know is your basic trig, your basic unit circle angles, at least the basics, like hopefully at least the pi over 2s. Pi over 4s and pi over 3s and pi over 6s would be nice too. And also the basic identity. And if you don't know those, here is your first opportunity for me to tell you, you should know them. And I will tell you which ones you need to know. The one that you should know for the rest of your life, you're 85 years old, your grandkids are over asking about your glory days in college. No, let me tell you about the Pythagorean theorem. Now, keep that in mind because we're going to be using it. Okay, so now the other part of your trig knowledge is that if I write this down, let's actually put a domain on this. Let's say t ranges between 0 and pi. And that way I can write down pi over 4s in here. All right, everybody in here should be able to produce that table real quick. And I say that not because I really care one way or another, but your life is going to be a lot easier if you don't have to start your exam by drawing a unit circle and labeling the whole thing and taking 5 minutes making sure it's perfect before you begin. Okay, sine of 0 is 0. Cosine of 0. All right, cool. Let's just do the rest of them. Root 2 over 2, 1, root 2 over 2, 0. In this column, we're doing cosines. Cosine of 0 is 1. Cosine of pi over 4 is root 2 over 2. Cosine of pi over 2 is 0. Cosine of 3 pi over 4 is minus root 2 over 2. Don't mess that up or you're going to get out the wrong shape. Cosine of pi is minus 1. Good. All right. I heard people say negative, but I didn't hear the one. Okay, so let's actually look at this one. What do we see when we plot that? So don't confuse the coordinates either. I'm very careful to arrange this in columns so I can read off. This is the point 0, 1. This is the point √2/2, √2/2, etc. So at 0, 1, that was at time is equal to 0. Then we're here at √2/2, √2/2. And then we're here at 1, 0. And then we're down here at √2/2 minus √2/2. And finally, we finish up right here at 0, 1. So I've got a shape that looks like this, putting my arrows on so that I know which direction things are moving. What is it? The worst parabola in all of existence, or a half circle? It's a half circle. Because I'm going to algebraically solve it. So when you're looking at this, what you think is, so plotting by hand is always just sort of give you an idea of what's happening. It's never going to be an exact idea. So the idea that I have here is, sines and cosines are involved, and this looks an awful lot like it's doing a circly sort of thing, because these are exact. I'm not getting further away, and you could continue on if you wanted to put bigger values of t in, and what you would see is that it would wrap back around on itself like this. So even if you didn't know that, though, you've already got this parametric description of how this particle is moving, starting here and ending here. Now, I know that I've got x is sine and y is cosine. If only there was a relationship between sine and cosine that I could use to make into a relationship between x and y. If only. Oh, wait. I wrote it on the board in actually the perfect spot. So when you got sines and cosines mixed together and you're trying to eliminate the parameter, you can't just get rid of the t, you've got to get rid of the sine and cosine. Those aren't going to carry through as the answer, right? The t is wrapped up in these trig functions. But if you notice that x is equal to the sine of t, y is equal to the cosine of t, then this equation right here turns into x squared plus y squared is 1. And as every brain battered middle school algebra student working on conic sections knows, the circle has the equation x squared plus y squared is equal to r squared. Now again, this guy right here, in many ways, is harder to work with than the parametric equations that describe it because it's not a function. You want to take the derivative of this, you have to use implicit differentiation. Okay? It doesn't even really have a domain. It just has a set of points that are associated by the formula because the circle is not a function. So it's typical when you're working with these sort of setups that things with sines and cosines turn into circular type objects, but not always. And this application of the Pythagorean identity, that's typical of what we're going to be doing. Parametric equations are going to require that you remember at least the basic associations between the trig functions. Let's do one more. And the next time we'll talk about how to do calculus in this setting. Yeah, I did this one last time, I think. Okay, so let's consider almost the same problem. Okay, so this time I'm going to restrict my domain to the whole 0 to 2 pi. Actually, let's make it a little more interesting. Let's make it 0 to 4 pi. Oh, 2 pi. Not going nuts. We're at the beginning. Okay. Any guesses as to what's going to happen here? I mean, and that's true. Suffering. So I guess the first thing is that one of the complications with parametric equations is that a lot of the intuition that you have about the way functions work in Euclidean type settings where you have functions of x and y is that these are technically independent from each other, right? X of t and y of t are moving independently. And so things that look like things you already know, like, oh, look, I just shifted one of the coordinates, right? The problem is that that shift might not actually correspond to a shift that you're used to from shifting functions that look like y equals f of x, because these are acting independently. Yep. Okay, yeah, if you've seen this. Yes, yes. Okay, so we're doing vector calculus without doing vector calculus right now. Yeah, okay, so here, so we'll brief this, I'll do a tiny excursion of people who've seen the set of settings. Really, this is a function x of t that's taking r into R2. If you've seen this setting before, this is a vector equation. If you have not seen this before, this is waiting for you in calculus 4. And at the and maybe at the very end of this class, but Calc 4 is about this. But the idea is, yeah, you can think about this as a vector equation. So we're doing vector calculus by pretending there's no vectors. Okay. Well, I'm just going to do it before, but now I'm going to make the laziest table possible. 0, pi over 2, pi, 3 pi over 2, and 2 pi. And I'm going to hope I can figure out what's going on for these really easy to compute angles. And then if I can't, I'll fill in the angles in between. But at the very least, I should be able to figure out the easiest possible answers, values that come out of sine and cosine. All right, x and y. X of 0 is sine of 0. That's the same as before. Sine of 0 was 0. Sine of pi over 2. 1. Sine of pi. 0. 3 pi over 2. And 2 pi. Perfect. Okay, how about 1 minus the cosine of t? 1 minus the cosine of 0. 1 minus the cosine of 0 is 1 minus 1, which is 0. 1 minus the cosine of pi over 2. Cosine of pi over 2 is 1 minus 0 is 1. Cosine of pi. So it's 1 minus negative 1, which is 2. Cosine of 3 pi over 2. 0. So it's 1 minus 0, which is 1. Cosine of 2 pi. 1. That's fine. You're just skipping to the answer, right? Okay. So let's take a look. Maybe we can figure out what's going on just from this part of the table. So I've got a point 0, 0. At t is equal to 0. I have a point 1, 1. At t is equal to pi over 2. I have a point 0, 2. Oh, wait, I see what's going on. At t is equal to pi. And then there's going to be this point, which was minus 1, 1. And then we come back around to 0, 0 again. So this looks like this. At least we speculate, because I only drew 4 points, right? So I'm basing a graph off of 4 points. Clearly, the most rigorous way to do a graph is off 4 points. How can I prove that this is a circle? Well, numerically, I can just fill in more points in the table and it would trace this shape out, right? Man, I got these sines and cosines and I got this circle right here. How can I? Well, that work. It's been a long day. Gods of the chalk don't like me right now, and I'm in a barbarian spot over. All right. Sine squared of t plus cosine squared of t is 1. I can use that. Can I somehow mix this together with this information? Well, this is easy. Oh, look, that I could just put up right here for an x, right? I want to get the t's out, and I know that sine t is equal to x, so I could rewrite this as x squared plus cosine squared t is equal to 1. But now, how am I going to get rid of that and do something with the y value? Yeah. I mean, add cosine, subtract y, you get this expression, right? Ah, okay. So, I mean, yeah, if you want to, I guess, but then that doesn't get y. You're going to get some identity in x if you do that. The idea is you need to somehow use both of these for the substitution. So it's a good idea, but if you do, you're just going to get 0 equals 0. When you're done doing all your substitution. So cosine of t is 1 minus y. This turns out to be this. You might ask, well, 1 minus y minus 1, why can you do that? It's because there's a square out here. And I put it in this form because somewhere deep in the recesses of your brain is the formula, a tutor or a teacher repeatedly telling you x minus h squared plus y minus k squared is equal to r squared, sort of shifted circles with center hk. Like, yeah. Every class I get somebody that's like, oh my God, yeah, I remember how bad that was. Anyway, so yeah, this is a shifted circle. This is the equation of a circle of radius 1 whose center has been shifted 1 unit up. Okay. So in this case, it's fortunate that we can do that. It is not always the case we can do this. And again, to emphasize once more, we have thrown a ton of information away to do this. For example, that thing, I could make that wrap around the circle more than once. It would have been a different question if I had said t went from 0 to 4 pi. Because that would say it traveled around the circle one time and then it went around the circle again. And that's a different path than just going around once. The curve they sweep out is the same, but the path is different. So the reason that matters to us is because if I want to know how far the object went, I have to know how many times it wrapped around the circle. And that's going to require working not with this form, which tells us about the path after thinking about a snail traveling. This is like looking at the track the snail left behind versus actually watching it in progress. To figure out things like distance and speed, we're going to have to work with these equations. And that's where we're going next time. All right, that's it for the day. Thanks for your attention. Thanks for your hard work on that test. And